Chapter 7, here we are. You know a lot about square roots already. We're just going to learn some terminology, make sure we're all speaking the same language. Talk about a principal square root. Basically, when we talk about a principal square root, we're talking about the positive square root. We're also going to talk about odd and even kth roots. Well, we could say that a square root is the second root, couldn't we? We could also talk about a cube root, better known as the third root. We could talk about the fourth, the fifth, the sixth. You get it now, don't you? This is why they're saying, and k is simply standing for whatever integer we want to put in there. And we have odd ones. Odd, oh, that doesn't show up. Odd ones, oh, that doesn't show up either. All right, we have odd ones. There's an odd one. There's an odd one. No problem. So we're getting ready for doing multiplication and division of radical expressions. Fancy stuff we're coming up to. Can we factor 121? Well, yes. I don't know if this jumped out at you immediately, but that's 11 times 11, which we could write as 11 squared. Or, did you think of another way this could be factored? It could be 11, but negative. Negative 11 times negative 11, negative 11 squared. Can we factor this? Well, here we have a quadratic trinomial, 1, 2, 3 terms. We know that those often can be factored into two binomials. Clearly it's got to be x and x to get to x squared, and let's try 10 and 10. That would give us the 100. The only question we have is our middle term. To verify that this actually works, we'll go ahead and FOIL this. First, multiplied together gives us x squared. FOIL, oh, outside, plus 10x. Inside is another plus 10x. And last, which is 100. We simplify this, we get x squared plus 20x plus 100. So we have verified this. This could also be written as x plus 10 times x plus 10. Solve for x. There's the x, where we've got 4x squared equals 9. Of course, we remember that when we're solving for a number, or excuse me, for a variable, we want to isolate that variable. That's already been done. It's here. It's got nothing added to it. But it doesn't have a coefficient of 1. We want a coefficient of 1. This is being multiplied by 4. We're going to do the opposite operation. We're going to divide by 4. What we do to one side, as long as we do it to the other, the equation will remain true. Now I've got x squared equals 9 divided by 4. And one of the things I hope you are noticing here is that 9 is a perfect square. 3 times 3. 4 is a perfect square. 2 times 2. And since we're about to do square root in order to find x all by itself, that's going to be important to us. If we take the square root of both sides, remember, as long as we do the same thing to both sides, it's good. However, there's an extra wrinkle here. We have to think about the fact that this could be either positive or negative. Because if we square something which is negative, it becomes positive. So we have to, anytime we do something like this, where we take the square root of something, on the other side of the equation, we have to say plus or minus. Now we've got x, because the square root of x squared is x, is plus or minus the square root of 9. I'm going to rewrite it like this. This is equivalent, just because I think it makes it a little easier to see. X equals plus or minus 3, which is the square root of 9, over 2, which is the square root of 4. There's our answer. The terminology, a radical expression. Let's be clear about what a radical expression is. It has the radical sign, and whatever is underneath that radical sign is called the radicand. You're going to hear me using that term quite a bit. When I say radicand, I'm talking about whatever is underneath the radical sign. When you see a radical sign with no negative in front of it, you're actually seeing the positive. And we call this the principal square root. Now, we don't write that positive there, but we know from our experience that it is positive. How do we know this? If it were negative, it would have a negative in front of it. All positive numbers have 2 square roots. For example, 4. If we take the square root of 4, what would that be? 2 times 2. So the square root of 4 can be 2. But when we look at this positive number 4, it could also be factored this way. So we can also say the square root of 4 could be -2. In which case we would have to say we're talking about the negative square root of 4. The positive square root of 4 and the negative square root of 4. Okay, so we know this as the principal or positive square root, and we know this one as the negative. We're going to use an example here which is not a perfect, well, I guess it is a perfect square. It's 25, but we're going to say, what if we have a -5 and we square it, and then we take the square root of that? We'll always start inside first. So we've got the square root of -5 times -5, positive 25. And that, of course, would be 5. That's a positive here. And then the square root of 5 times 5, which is also equal to 5. It's a positive square root. This is a positive square root. When x is equal to -5, the square root of x squared, we just proved it up here, is 5. When x is equal to a positive 5, the square root of x squared is also equal to 5. This is my way of bringing you to this general rule right here that anytime you're taking the square root of something squared, it's exactly the same as taking the absolute value of whatever is being squared. In this case, it was 5. Whether you had a negative 5 or a positive 5, you got a positive 5 out. Why? Because when you square something negative, it becomes positive. So general rule, this is going to equal the absolute value of x. How many principal square roots does negative 2 have? Oh, this is like a trick question, isn't it? Let's go back and let's see if we talked about this at all. All positive numbers have 2 square roots. What have we got here? We've got a negative number. We are not going to take the square root of a negative number. No. What is the greatest number of principal square roots a number can have? Principal square roots? How many positive square roots can a number have? 1. It has 1 principal and 1 negative. Now, here's a conceptual question for us. If we square negative x and then take the square root of it, what have we got? When we square a negative x, we get x squared, don't we? And over here, when we square positive x, we could take it a little further, although I think we've already proved our point. We know that the square root of something squared is the absolute value of that. So the answer here is yes. For what values of x? Oh my goodness. For what values of x does the square root of negative x equal the square root of x? Now, didn't we say we couldn't do? We had to use a positive radicand. There's the word. We had to have a positive radicand. So is there any number that we could use here? What if x equaled 0? That would work, wouldn't it? Square root of negative 0 isn't actually negative, is it? It's the square root of 0. And square root of positive 0. So I would say only 0. When you have questions like this, I recommend to you think about what if x were greater than 0? What if x were less than 0? In other words, you think of a positive value and you think of a negative value. And when I challenge you, think of as many of those as you can, and it's never going to work. But always remember, you also want to test 0. And sometimes 0 will work where nothing else will. Find 2 square roots for each of the following numbers. 2 square roots of 100. 2 square roots. We're going to take the principal square root, which is 10. And what's the other one? That's right, negative 10. If we were to square this, we'd get 100. If we were to square this, we'd get 100. How about this? A 1. 1 is such an interesting number, isn't it? It doesn't matter whether you say 1 squared, 1 cubed, 1 to the 4th power, or you start taking the roots. the square root of 1, the cube root of 1, the fourth root of 1, it's 1. But in the case of an even root, like a square root, we also have a negative 1. How about 5 squared? 2 square roots for each of the following numbers. Okay, 5 squared is equal to 25. We have to work that out first before we can answer this question. Now, 2 square roots of this, we're going to have 5, and we're going to have negative 5. Simplify this. Now notice this is already talking about one of the square roots. Which one? That's right, the principal one. So in this case, we're only talking about the principal square root of 1. In this case, we're looking at the negative square root of 4. So that's going to be a negative 2. In this case, we're looking at only the positive, the principal. Principal square root of this would be equal to right? Another way to look at this one, is a way I prefer to look at it, is 1 over 100. Somehow that seems a little easier to me. Square root of 1 over the square root of 100, which I know is going to be 1 over 10. Now, this is an interesting one. Ordinarily, what do we say here? We say we can't have a negative number, but this isn't a negative number, is it? It's not a negative number. It's the square root of, oh my goodness, a negative times a negative is a positive. What's 17 times 17? Excuse me while I do a little manual stuff here. That'd be 49, add 4, I get 11 and 17. So I end up with 289. So this is the positive or principal square root of 289, which is, since this is a perfect square, a positive 17. These are getting really interesting. Who knew that a simple radical could be so much fun? All right, let's look at this one. This is the square root of, let's multiply this out, 2x times 2x, right? When we square something, we multiply it times itself, which gives us 4x squared, which is the same as, I just want to give myself a little more room here, which is the same as the square root of 4 times the square root of x squared. Now, this is an interesting situation because we don't know if x is positive. Is it representing a positive number? Is it representing a negative number? It could be either, right? 4 is clear. 4 is very clear. That is the positive square root of 4, or the principal square root, which we know is equal to a positive 2. In the case of this, oh, let's go back to our, remember we had a general rule. When you take the square root of a variable, we don't know whether that variable is positive or negative. It's being squared, which tells us that whether it is, even if it is negative, it's allowable because when we square a negative, we get a positive, and so our radicand is positive. We can say this is the absolute value of x. Whatever x is, we'll take the absolute value of it. What about this one? That's the same as saying the square root of x squared, which is also the absolute value. And please notice that in all of these cases where I'm putting this mark in, I probably shouldn't do that because it might be confusing. Oops. instead of putting a mark there, I'm just going to notice. Wants to draw a straight line, I guess. I want to do a circle. I'm just doing this in front of all these that have no sign, because no sign in front of it means that it is positive. And I want to emphasize that right now. Okay, now for this one, this is going to be the positive square root of however this factors. Now this is a perfect square trinomial. You can prove it. I'm not going to take the time for that right now. We are saying the square root of x plus 5 squared. The tricky thing here is I don't know whether this expression is going to be positive or negative. So I'm going to have to say the absolute value of positive, but absolute value of x plus 5. Because what if x were, for example, negative 7? I have to take the absolute value of this. All right. Radical expressions. Now, we've been recognizing that this is the square root. We certainly have recognized that it is the principal square root, because we know when we don't see a sign here, that means we're talking about positive. The other thing I want you to learn is that when we don't see any number here, it means we're dealing with a square root. We don't write it in there, but we know it. It's an even root. When we have an even root, we run into this situation here, that if we raise x to that power and then take the even root of it, we have to say the absolute value of x is a result. Even roots can only have positive radicands. There's that word again. Odd roots are much more forgiving. They allow you to have negative or positive radicands. So we're not going to run into this situation with an odd root. Now, what do we call this number that tells us what the root is? We call that the index. So that's a new word for us to pay attention to. The radical sign, the radicand, and now the index. Let's simplify this expression. Oh, 1 is such a beautiful, beautiful root to do, isn't it? It's going to be a negative 1. Now, if you need to prove that to yourself, we could go the other way. Say, okay, if negative 1 is the cube root of negative 1, then if I cube this, I should get negative 1. And let's see what happens. Negative 1 times negative 1 times negative 1. These two, what happens? I get a positive 1, right? And then I multiply it by a negative 1, and I end up with negative 1. Okay, we're good. The cube root of x cubed is x. Do I need to put in absolute value? No, because this is an odd root. How about this one? This can be written just like we did for square roots. Just remember to put your index in there when you do this kind of thing. Because if you don't put it there, what does it mean? It means a square root. That would be misleading. What is the cube root of 8? So here we're trying to think of something which multiplied by itself time and time again would give us an 8. Actually, it's going to be helpful for you to learn some of the cubes. Let me show you a couple of them now. 1 cubed equals 1. Also, why don't I put the negative version of that right here? Negative 1 cubed equals negative 1. 2 cubed is 2 times 2, which is 4, times 2, which is 8. Negative 2 cubed is, right, 3 cubed. 3 times 3 is 9, times 3 again. So a negative 3 cubed, negative 27. And let's do one more. We probably should keep on going, but in the interest of time, I'll just do this. You can do more for yourself if you want to. 4 times 4, 16 times 4, 64. And a negative 4 cubed is a negative 64. These would be really good to get familiar with so they can come to you quickly. This then is 2 over 3. See how quick it is if you happen to know that 8 is a perfect cube and 27 is a perfect cube. Same thing here, it's pretty quick to do if you recognize your cube root of 27 is 3, and of course the cube root of x cubed is going to be x. All right, how about this one? We have 1, 2, 3, 4, 5 zeros. Well, just for consistency, let's look at another example. Suppose I had the square root of 100 with 2 zeros. What would that be? Now I'm only interested in the principal square root, so that would be a positive 10. Turns out with 1, 2, 3, 4, 5, taking the fifth root, it is also 10. You can prove that to yourself if you like. Fifth roots. Well, it would be nice to know all the powers of 2 up to some, because they're used so often. Let's take a moment for that. 2 squared is equal to 4. 2 cubed, we've already talked about. Oops, yeah, we'll do 2 cubed, which is 8. 2 to the 4th power, so we just multiply that by 2 again, right? Gives us 16. 2 to the 5th power, which is the one we're looking at here, you multiply it by 2 again, which gives you 32. 2 to the 6th power would be 64. Be careful. Notice how I let this slip down a little bit. That could be confusing. Somebody might read that as 26 and they'd say, that's not true. 2 to the 7th power, you can see how this works. It just keeps doubling. 2 to the 8th power, and so on. So 32 is a perfect fifth root because of this. Let's see, we can say this is going to be 2. Negative 1, we know about this one. No matter how many roots or powers you take it to, 1 and negative 1. always stay the same. At least with odd roots, you can do this. If this had been an even root, we couldn't have used a negative as part of the radicand. Now, what's happened here? This time, I'm taking a negative, right? Here it is, a negative. And I've got a negative radicand, but that is okay, just as it was here, because this is odd. If the root is odd, you can deal with a negative radicand. Up here we knew that the fifth root of 100,000 would be 10. So here we're taking the negative fifth root, and the fifth root is a negative 10, isn't it? But since we're taking negative of that, or you might think of it as minus a negative 1 times that, and it turns out to be a positive 10. So think these through carefully. They look very simple, but they actually take some fairly sophisticated thinking. Let's see how far along we are. Oh, this is our last one. You're probably happy about that. I'm a little sad. They've been kind of fun to do. Okay, what would be the seventh root of this? Well, I'm going to do a little trick here. We're going to say x squared. I'm going to do power of a power. Isn't that an equivalent expression? X to the 14th, I could say it's the same as, oops, don't you do that. I forgot to put the index in. Now it becomes a little easier, doesn't it? It's an odd, so I can just say it's square. I was looking for the positive. On all of these except number 13, I'm looking for the principal root. Okay, let's look at this one. What happens here? This is an odd root, so I don't have to worry about the radicand being negative. It'd be okay if it is. So my answer here is simply a plus 1. The sixth root of 64. Whoa. Let's look back here to my little table that I made up. 2 to the 6th power is 64. Very good. We can use that here, can't we? So it's positive 2. What about the 6th root of negative 64? We cannot have a negative radicand when your index or root is even. Okay? So this one we would say, for now we would say no solution. Later on in this chapter, I think, I hope, is it in this chapter? We're going to find out how to deal with this. But right now we're going to say no solution. We do not allow a negative radicand when the index is even. That's not the case here. We've got a positive radicand. Oh my goodness. What is the fourth root of 256? I'm actually going to go back here to see if I can help myself out. 2 to the 8th would be the same as 2 squared to the 4th, right? Which is the same as 4 to the 4th power. See how handy this little table is? So I saw the 256 and I thought, I've seen that before. But in this case, I wanted the fourth root of 256, which would be 4. So I don't want the principal root now, I want the negative. 4. Ooh, what do we got here? Well, this is okay. The 6th root of 2 to the 6th is going to be 2. We know we're talking the positive here. And then I've got the 6th root of x to the 6th. So what is this? This is a case where we have to use absolute value because we cannot allow, this has to be positive when we take the even root of an even power. This one's a little bit interesting. Let's see if I can express it as a perfect power of 4. Let's see, yes, I think I can. We can say x minus 1 squared to the 4th power. So then, when I take the 4th root, I get x minus 1 squared. Now, do I need absolute value here? I do not, because even if this is a negative expression, I'm squaring it, so it will become positive. When you're squaring a negative, it becomes positive, so that's okay. We are done in 36, 37 beautiful minutes.